Okay, test. Good. The Zoom sound also okay? Okay, so then I'll continue with my third hour of lectures. And what I want to talk about in this hour is the Fourier transform, the quantum Fourier transform, and an application of the quantum Fourier transform. And this is really setting the stage for my explanation of Shor's algorithm for fast integer factorization for tomorrow. But it's kind of a beautiful thing in itself also. I think the Fourier transform is just like super useful everywhere. If you're a mathematician, you probably agree. If you're an engineer, you probably also agree. If you're a physicist, you probably also agree. So let me start with just the Fourier transform. I'm going to talk about the discrete Fourier transform, so finite dimensions. So this is a linear transformation that sort of shuffles around a vector in a way as much as it can. And let me just define what I mean. So I'm only going to talk about the, like I said, the finite dimensional, let's say capital N dimensional. Let me just write down the matrix for the Fourier transform. So this is going to be a capital N by capital N dimensional matrix. And I'm going to index the rows and the columns of this matrix by J and K respectively, where these are integers that range between 0 and capital N minus 1. So I'm a theoretical computer scientist, and that means that I number things starting from 0. Right, so both K and J are between 0 and capital N minus 1. And the entry, the JK entry of this matrix is defined as follows. So I'm going to define a capital Nth root of unity to be e to the 2 pi I divided by capital N. Now, why is this called an nth root of unity? It's because if you raise this object to the power capital N, you get back 1. And it's good to kind of have the unit circle of complex numbers in mind here. So omega n is a number on the complex unit circle, and its powers are also numbers on the complex unit circle. Okay, this circle is a little bit ugly, but okay. So omega n would be sitting somewhere here, let's say. And if you start powering omega n, you're sort of traveling around this unit circle. So omega n squared would be sitting here. Omega n cubed would be sitting here. And you can see it's almost like the sort of like the dials of a clock. If you power this root of unity, it sort of takes you all around the unit circle. There's a nice property here that if you sum the powers of this root of unity, say from j running from 0 up to capital N minus 1 of omega sub n to the power j, this is exactly 0. And you can sort of see it from this picture. If you're adding up all these vectors, you know, like the positive and the negative imaginary parts cancel to 0, and the positive and the negative real parts also cancel to 0. Okay, so this is a complex number of unit norm. And the entry I'm going to put on the jkth position of my matrix is the product, sorry, is the power, the j times kth power of this root of unity. And you should think of jk in the exponent here as the multiplication of two integers. And I'm going to divide this thing by square root of capital N, because that's what will make it unitary. Okay, so let's sanity check, first of all, that this matrix is unitary. Later on, I want to interpret it as a quantum operation, so it better be unitary. And if you want to check that such a matrix is unitary, one way to do it is just to check that the columns all have norm 1, and that two different columns are pairwise orthogonal. Now, every column here, if you ignore this normalization briefly, then the magnitude of every entry here is 1. But it's really divided by square root of capital N. So if I look at the squared numbers here, they're all of magnitude 1 over capital N, which means that if I sum it up over one column or also over one row, I get 1. So all the columns and all the rows are unit vectors. They're properly normalized. And using this property here, it's kind of easy to see that two different columns have inner product 0. So this is a unitary matrix. For now, it's just a unitary matrix, but of course, like 5 minutes down the line, I'm going to interpret this as a quantum operation. But even without quantum, this is a very important unitary matrix. And the reason that it's important is that you can apply this matrix quite efficiently to a given vector. So we can compute the matrix vector product Fn times V, where V is some vector of real or imaginary or complex entries of dimension capital N, and this is a capital N by capital N matrix. You can compute this in time order n log n using the so-called fast Fourier transform, FFT. This is all classical, what I'm saying here, classical algorithms. And this is kind of surprising, because if you think about sort of naively computing the product of a capital N by N matrix with a capital N dimensional vector, then each entry of this matrix vector product is an inner product between a row of Fn and an n-dimensional vector. Just computing one entry of this matrix vector product would already take you time capital N. Computing it for capital N entries separately seems to take time capital N squared. But there's a clever way to do it. That's this fast Fourier transform, dates from the 1960s. It was voted as one of the 10 most important algorithms ever. So the fast Fourier transform allows you to multiply the Fourier matrix with a vector in almost linear time. N log n is just a little bit slower than n. And this is very important in, for instance, signal processing. So you use it in signal processing to take some sort of wave, for instance, it's like a piece of music, and to sort of decompose it into the separate frequencies. And the more quickly you can do that, the better. So the fast Fourier transform allows you to do that. It's used for data compression. And it's used a lot also in theoretical computer science as a tool for analysis. And there's probably many other applications in engineering, also in machine learning, where the fast Fourier transform is super important. Okay, but this is all classical. And now I want to make the step to quantum. Right? This is a unitary matrix, so we can interpret it as a quantum operation, an operation on a capital N dimensional space. And if we take capital N a power of 2, like 2 to the power little n, then this Fn is actually an operation on a state of little n qubits. And a very useful one also. So what does that mean? Like, for instance, if I were to write it as a map on basis states, it looks like this. If I take Fn and I apply it to a basis state, cat k, where I'm thinking of k as either an element of 0, 1 to the little n, or as an integer between 0 and capital N minus 1. I hope this is not super confusing. Like I always notice when teaching for a mixed audience that like the non-CS people are very confused about binary notation. I hope it's kind of clear how sequences of zeros and ones represent integers. Is this clear? Should I explain it maybe? So let's say if you have a bit string k, let's say k1, k2, up to k little n, these things are bits, then this represents an integer in the following way. And the integer that it represents would be 0 to little n minus 1 of 2 to the n minus, sorry, let me run it. And this is just sort of a complicated way of saying that the different bits that are present in this number, they indicate which powers of 2 are included in this integer. And maybe an example is actually clearer. So suppose that little n is 3, and my bit string is this one here. So what integer does this represent? 4. And why is that? It's because the first bit corresponds to 4. The second bit corresponds to 2. The third bit corresponds to 1. And out of these powers of 2, the only one that is present in this number is the first one. So this represents the integer 4. Let's take another example. K equals 1, 0, 1. Which integer does this represent? Hint. This is 5. Right? Because we're adding 2 to the power 0, which is 1. Okay, so whenever I write something like cat k, I'm thinking of k as a string of little n bits, but I can equivalently think about it as an integer between 0 and capital N minus 1. It's very important here to sort of keep the little n and the capital N apart in your mind. In any case, what is the state that you get if you apply the Fourier transform to this cat k? This is just quantum notation for the kth column of the matrix. I don't think I'm telling you anything that you don't know already, but I might do it in a notation that's a little bit confusing initially. So this is a good time to ask questions if people are confused. Okay, so in any case, this big matrix here of dimension 2 to the little n by 2 to the little n, it's an operation on little n qubits. And whenever you have an operation on little n qubits, you can ask yourself, how efficiently can I implement this using elementary gates? So operations on 1 or 2 qubits at a time. And the beautiful thing here is that this operation actually has a very efficient implementation as a quantum circuit with not too many gates. So Fn can be implemented by a circuit that uses only order of little n squared many gates on 1 or 2 qubits. And I'll sketch in not too long how this actually works. Point is, this is a very efficient circuit. You can even make it a little bit more efficient. You can make it even order n log little n gates if you allow a tiny error. And now you might say, well, poo, you know, we had this fast Fourier transform, it had complexity n log n, and now we have a quantum Fourier transform and it has complexity n log n measured in terms of gates. But notice that we switched from capital N to little n, right? This is actually, in some sense, exponentially better than the classical fast Fourier transform. But at the same time, it's not really comparable to the classical fast Fourier transform because it's doing something different. What the classical fast Fourier transform does is you give it a vector of dimension capital N, you write it down on a piece of paper, and it very efficiently writes down on another piece of paper or maybe in computer memory the capital N entries of this vector. This is not what the QFT, the quantum Fourier transform, does. What happens when you apply the quantum Fourier transform is somebody gives you a state. This state has little n qubits and therefore capital N amplitudes. It's represented by a vector of dimension capital N. The vector of dimension capital N is being Fourier transformed. And what you're getting back is another quantum state of little n qubits whose amplitude vector would be this. But you neither start nor end with an amplitude vector written down on a piece of paper. You start and end with an amplitude vector of a state. So in some sense, the quantum Fourier transform is exponentially faster than the classical fast Fourier transform, but it does something very different there. They do incomparable things. The QFT, even though it's the same matrix, when you think of it as a quantum operation, it does something that does not have a classical analog. But it is actually a very useful thing. Questions? Okay, so I want to do two things in the remainder of this hour. Let me see how much time I have. Okay, it's 30 minutes almost, it's good. So I want to explain how this efficient quantum circuit works, how you can sort of use the structure in the quantum Fourier transform to write down a very short circuit to actually implement it as an operation on little n qubits. And then I want to explain how to use it to do something called phase estimation, which is an important subroutine in many quantum algorithms. So how to implement this unitary efficiently? Maybe we should start with small cases here. Small cases first. And what is the smallest case? The smallest case is little n equals 1. Right, so what is the quantum Fourier transform on only one qubit, right? If you look at that definition, what would be this root of unity? So if little n equals 1, then capital N equals 2, and this thing would be e to the pi I, which is -1. And if you just plug that in here, what matrix do you get? It's something we've seen before. It is the Hadamard gate. So F2, the two-dimensional Fourier transform, aka the one-qubit Fourier transform, just is the Hadamard gate. Now this, of course, is easy to implement as a circuit. You just apply the Hadamard gate and that's your circuit, right? So like the simplest small case is easy to do. Let's look at the next case, little n equals 2. So if you look at what happens on a 2-qubit state, or in fact, more generally, there is structure in this superposition here. And there's almost magical structure, which is that this complicated looking superposition here, this is actually a product state of little n qubits. So let me write that down here. I'm going to write it down without proof. You can look at the calculation in my lecture notes. It's just kind of tedious. I don't want to do it on the board here. So if you apply the Fourier transform to a basis state ket k, I claim that this is a product state, and I'll write down that product state for you. So this is, let me get this right. This is the following product state. 1 over root 2, 0 plus e to the 2 pi I. And then, so I'm thinking of k here as a string of n bits. So what is this object here? This object is sort of like the ket plus state, except that it has an additional phase in front of the ket 1. And that phase only depends on the last bit of k. This is the first qubit of the result that you get when you apply the Fourier transform to the kth basis state. And then the second qubit of this QFT basis state has something where the phase depends on the last 2 bits of k. So what is this here? I'm again using binary notation now, but now behind the decimal dot. So just to tell you what this means, 0 dot kn is kn times 2 to the minus 1. In other words, it's either 0 or a half. 0 dot kn minus 1 kn is kn minus 1 times 2 to the minus a half plus kn times 2 to the minus 2, etc. So this is binary notation, but then of sort of numbers between 0 and 1. So, and the point is that this number here, which is either 0 or a half, only depends on the last bit of k. And this number here, which is either 0 or a quarter or a half or 3/4, it only depends on the last 2 bits of k. And it goes on all the way until the last qubit, which depends on all of the bits of k. So I have not proven this equality here, but just believe me, or look up the derivation in the lecture notes. This state here is actually a product state of relatively simple qubits. Like each of these qubits here is sort of like the ket plus state, but then with some extra phases rotated in front of the ket 1. And these phases have a very clear dependence on subsets of the bits of the string k. So this is something we somehow want to realize as a circuit now. So let's get back to small cases, the case of, let's say, the 2-qubit Fourier transform, the 4-dimensional Fourier transform. Right, in that case, my basis state k only consists of 2 bits. And what is the resulting product state that I want to produce? I'm sorry, this should be K2, I think. Right, so when I want to implement the 2-qubit Fourier transform on a basis state, I just want to produce these 2 qubits here, both of which are like ket plus states with a tiny bit of correction on the phase of the ket1. And let's look a little bit closer at that at what that correction is. So what is this number here? This is a question to you about understanding binary notation and also about understanding complex numbers. This is actually a very simple number. What is it? Sorry? It could be a 1. For instance, if the bit K2 is 0, then this number would be a 1. But what happens if the bit K2 is a 1? Then you would have e to the 2 pi I times a half, which is e to the pi I, which is minus 1. So this number here, what is it? It's plus 1 if K2 is 0, and it's minus 1 if K2 is 1. Right, so this is either the ket plus state if K2 is 0, or it is the so-called ket minus state if K2 is 1. So just to sort of ignoring the rest of the qubits, how can we prepare this qubit here if we start with a circuit that has, like, on the left, the 2 bits of a basis state? How can I prepare this qubit here? Like, what do I need to do to one of these 2 wires? For this guy, you don't even need a control because it really only depends on one of the bits, namely K2. Right, so what happens if you apply a Hadamard gate to this guy here? I'm sorry, I should write this differently. Plus 1, K2 is 0, minus 1, K2 is 1. If I apply a Hadamard gate here, what am I getting? I'm getting exactly this qubit here. I get ket plus if K2 was 0, and I get ket minus if K2 was 1. Of course, this guy is in the wrong place, right? This is now the second qubit, whereas in the state that I want to produce, it should be the first qubit, but we'll fix that with a swap gate at the end. So we're making progress here, right? We're trying to implement the Fourier transform on basis states ket k, which of course is sufficient to implement the whole Fourier transform by linearity. So it suffices if you get it right on all basis states ket k. And so far, we've produced one of the 2 qubits that we need to produce for the Fourier transform, namely this one. And this was the easier of the 2 because this guy only depends on K2, while this guy depends on both K1 and K2. Okay, so now let's look at this number here. What is this? So this depends, there's like 4 different cases here, but it actually nicely factors into 2 pieces, e to the 2 pi I 0.K1 times e to the 2 pi I 0, 0, K2. Right, if you use addition in the exponents, you could see that this product of 2 different complex numbers is the same as this number that we want to produce here. So let's try to produce these 2 things separately. And let's first look at something we already know how to do. That's this guy. This again is just plus or minus 1, depending on the value of the bit K1. So this is plus 1 if K1 is 0, and it is minus 1 if K1 is 1. So if this thing were not here, then we know how to do. You just apply a Hadamard gate to this guy, and you would get the correct phase. But we need this correction term here, which is sort of a more refined phase that also needs to be plugged in, and it depends only on K2. So now what we're going to do is we're going to do a Hadamard gate on K1. That already gives us the correct phase when K2 was 0. And now we need to do an additional correction depending on K2. So this phase should be applied to the first qubit, this qubit. To the first qubit if K2 is 1. So what that suggests is that we now, at this point in the circuit, we do some controlled operation that's controlled by the value of K2. So something should only happen if the value of K2 is 1. And here we do something that adds a phase e to the, what is it? So 0.01 is the same as a quarter in binary. So we want a phase here that's like e to the 2 pi I times a quarter. And this is a very simple gate, and you can do it controlled on the value of K2. And what this does is that the first qubit here is now the second qubit that we were trying to prepare. Let me just write quotes underneath of it. Right, and that means that we've almost produced the product state that we wanted, except that the two qubits are in the wrong order. So we're going to end by a swap gate. Okay, my board is slightly over full now. So I'm just going to do a swap gate where these two qubits are put in the opposite order, and therefore we end up with the state that we want. And this works for every basis state, for every ket k of 2 bits. This is a subtle thing, but I hope sort of the structure is clear. Because of this, because of the fact that the Fourier basis states are products of individual qubits, it suffices for us if we can sort of produce those individual qubits, which are somewhat complicated functions of k1 and k2 up to kn. And that means that controlled on these values of k1 and k2, etc., we have to put in the right phases. And that's exactly what this circuit does. And let me also just write down the circuit for n equals 3. And you will probably see the structure of the circuit appearing. And then we'll count how many gates we're actually using. So what does it look like for n is equal to 3? So now we start with a basis state of 3 bits. K1, K2, K3. And the simplest of the 3 qubits that we want to prepare is really just, again, a Hadamard gate applied to K3. I'm going to do it like this. This is going to produce the first qubit of the final of the product state that we're trying to produce. This, of course, is not enough. Now, we also want to get the middle qubit correct, and that's going to look very similar to this structure. So we're going to do a Hadamard gate and a controlled phase gate controlled by K3. And this is again going to be 1 e to the 2 pi I over 4. So this gets 2 of the 3 qubits of the product state correct. And this one here is the most complicated one because it depends on all the 3 bits, K1, K2, K3. We start with a Hadamard. And then we do controlled phase rotations depending on both K2 and K3. I'm not going to write out the phases here, but you could sort of guess what they are. And this is going to produce the correct 3-qubit product state, except again, the qubits are in the wrong order. So again, we're going to swap the first and the third with a swap gate at the end. And this is the circuit for the 3-qubit QFT. This implements the 8-dimensional matrix that corresponds to this when capital N is 8. And how many gates did this use? Well, there's little n qubits here, 2 in this picture, 3 in this picture, little n in general. And you can sort of see, if you understand the recursive structure, that on every one of the wires, we're going to apply at most little n qubits, maybe even only little n minus 1, because you sort of need to do these phase corrections, but only depending on earlier bits. So there's n wires, or n qubits. At most, n gates, maybe controlled gates per wire. So that's a total of order little n squared gates. Right, so that's polynomial in the number of qubits that we're acting on, and we think of this as an efficient circuit. So that justifies the claim that I wrote here. There's also the claim that I wrote here, which is that if you want to allow a tiny little bit of approximation error, you could even get away with only using like n log n gates. And the reason for that is that if you look at the gates that are applied on a wire, they are these finer and finer and finer gate rotations. And you know, if you look at something like this looks like 0.0 and then a bit. But if you go a little bit further, it's going to look like 0.00000 and then a bit. That's a number that's super close to 0. And if you have e to the 2 pi I times a number that's very close to 0, that number is actually very close to 1, which means that many of the conditional rotations along the wire are actually super close to identity. And you can drop these things. If something is very close to identity, you can drop it without changing the circuit very much. So if you keep only the log n most important rotations per wire, you get this more efficient approximate circuit. That's a total of order n, little n, log n gates. Right, there's still n wires then, but you only do something like log n gates per wire, so the total is only something like n log n, little n times log little n. Yes. You can do a +1 if you want, but that's really just that's just lower order. In fact, so how many swap gates would you need? It's essentially little n over 2. If I write order n squared or order n log n and I add n over 2 to it, that's the asymptotics doesn't change. Okay, any questions about this? So the short summary is the quantum Fourier transform, which is sort of a quantum interpretation of this big matrix, is very important in many cases, and it can be implemented by a very efficient circuit that doesn't use a lot of gates. Any questions? I see a lot of people seem to be a little bit bewildered, so help yourself, help your friends, ask questions. Is there anything on the online questions? Okay, so all of these things are written in more detail in chapter 4 of my lecture notes, so you can also read it there and actually check some of the calculations that I swept under the rug here. Okay, let me see how much time do I have right now. How much? 10 minutes, okay. Yeah, please do.
One rule in order to decide on which ones are the most important to achieve log n.
Sorry, say again?
What one should do in order to decide which ones are the most important to achieve log n.
Oh, this is about, yeah, let me repeat the question. Like, how can we decide which log n of the rotations to keep? So if you look at the rotations that are happening here, conditioned on earlier bits, the angles over which they rotate, they get smaller and smaller and smaller by factors of 2. So the log n gates that you keep are the ones with the biggest angles, because the ones with tiny angles are closer to identity and it hurts less if you drop them. I hope that answers the question. Okay, so let me spend 10 minutes to explain phase estimation, and then we're done with my lectures for today, at least. Is the angle okay for the camera? Yes, I will. I guess the whole thing shifted a bit. Good, yeah. Okay, good. Okay, so now I want to explain this thing called phase estimation. It's an inherently quantum problem, but it's very useful also when you want to solve classical computational problems. And the idea here is that somebody gives us the ability to apply a certain unitary U, and they give us one eigenstate of U. So we can apply a unitary U even many times if we want to. And we're given one eigenstate, psi of U. Right, now the fact that this is an eigenstate means that there's an eigenvalue. So U psi equals lambda psi. So this is an eigenvalue. And because this matrix is unitary, there's something special about the eigenvalue. Maybe somebody can tell me what is special about the eigenvalue. Exactly, it has magnitude 1. So this lambda here is on the unit circle, so we can write it as e to the 2 pi I phi, where phi is a number between 0 and 1. And this is called the phase. So the goal of phase estimation is estimate this phase phi, which is some number between 0 and 1. So this is phase estimation. It may look like a weird and abstract and useless problem, but I'm telling you it's very useful, and I will show you how to solve it efficiently using the quantum Fourier transform. So let me draw a circuit for phase estimation. So let's make an assumption that this number phi here, which is some number between 0 and 1, can be written exactly with n bits of precision. So assume for simplicity that phi is equal to 0 dot phi 1, phi 2, up to phi n. Right? So this is sort of like notation behind the decimal dot, but now in binary. So these are n bits, and this is really what we're trying to recover. If the number phi needs more than n bits of precision, then what I'm going to say still works, but it will have some error probability. The calculations are messier. So let's make this simplifying assumption that phi can be written exactly with n bits of precision. So then what my phase estimation circuit should do is it should spit out a number consisting of n bits. It should spit out an n-bit estimator that should approximate or maybe even equal this number here. So let's start with little n qubits, initially 0. And this set of qubits at the end of the circuit is going to contain my estimate of the number phi. And in the second register, so sometimes blocks of qubits are called registers in quantum computing. So this will be my first register here, and this is my second register. My second register contains my eigenstate psi. And I only have one copy of this psi, and I don't know how to make it. I cannot make a second copy. We have one copy of the eigenstate, and that's it. So I can only use one of these guys. I shouldn't destroy it. So I'm going to start by putting all the n qubits that will contain the estimate, putting those in a uniform superposition. And we know how to do that. We just use Hadamard gates on each of these little n qubits. Right, so the state at this point of the first register is now a uniform superposition over all the little n-bit integers j. And the second register hasn't changed yet. And now what I'm going to do, I'm going to interpret the number j here as an integer, and I'm going to use that to control how many times I'm going to apply u to the second register. So here I'm going to apply some complicated operation, which, because I'm kind of running out of time, I'm going to summarize it instead of writing it out in detail. I'm going to call it w. And what w does is, if you have the basis state ket j in the first register, and you have some state psi in the second register, then it's going to apply u j times to this psi. So you can think of the first register as controlling, in superposition, how many times j is applied to the eigenstate psi. Now let me analyze which state we have after this w operation. So what is the state? Or actually, let's just track the state again, like we normally do, tracking the state through the circuit. And so we start with 0 n psi. We do these Hadamard gates on the first register, identity on the second register. We get a uniform superposition over all the strings j of little n bits in the first register. We still have psi in the second register. We apply w. We get 1 over root 2 to the n, sum over j, ket j, and then u to the power j is applied to psi in the second register. And psi is an eigenstate, right? So we sort of know what happens if you apply this unitary j times. You get the jth power of the eigenvalue. So this thing here, this is really e to the 2 pi I phi raised to the power j, which is the same as multiplying with j in the exponent. So times psi. And so what you really have in the second register is some number that depends on j, some complex number, times the original eigenstate ket psi. We haven't thrown it away, it's still there. And this number here, this actually commutes with the inner product, so I can equally well write it in front of the ket j here. So I can write the state as 1 over square root 2 to the n, sum over all j's, e to the 2 pi I phi j, ket j, and then tensored with psi in the second register. And this is an interesting state here. So I'm asking you to stare at this for a second and to tell me what this state is. And maybe it helps if I rewrite e to the 2 pi I phi j as, that is a Fourier transform. So I'm now thinking of phi 1 up to phi n, this binary sequence, as an integer. And I'm telling you that this complex number here, which is the same as what's sitting there in front of the ket j, is the same as the capital nth root of unity raised to the power j times the integer corresponding to the bits phi 1, phi 2 up to phi n. Right, so we're almost there. The state is a Fourier transform of which basis state? look back here, right? Like, which k do we need to use in order to kind of recover this expression? It's the k that actually corresponds to the integer phi1, phi2 up to phi n. So this state here that we now have in our first register, this is the Fourier transform, dimension capital N, applied to the basis state, which consists of the n bits of phi. And this is what we want to know. We want to know these numbers phi1 up to phi n. What we have is the Fourier transform of that basis state. So what's the last step that we want to do here to recover phi1 up to phi n? The inverse of the Fourier transform. If you do the inverse of the Fourier transform, you actually get back the basis state cat phi1, phi2 up to phi n. You measure it, and lo and behold, what comes out is a perfect estimate of the number phi. And just to sort of wrap up a final thing, you might think, we have an efficient circuit for F1, but can I also just apply F1 inverse? And the answer is yes, because every quantum gate has an inverse, right? It's unitary, so it has an inverse. If you have a circuit expression for Fn, you also have a circuit expression for Fn inverse. You just do it in the opposite order, and you invert the individual gates, which themselves are also gates. So this can be done as efficiently as Fn itself. So this problem of phase estimation has a very elegant solution thanks to the Fourier transform. And there is, of course, something nasty here, which is that we're actually doing fairly high powers of u here, conditioned on the value j, because j can be quite big, right? The biggest j in that superposition is like capital N minus 1. So that's also the largest number of u's that we do. That's the expensive part of phase estimation. But in many cases, you can sort of get around it, including in Shor's algorithm. And I think I should stop here. The timing is very decent. Okay, so that's it in terms of my lectures for today. Any last questions? Yes, please.
Exactly an eigenstate.
Yeah, good question. So if it's not exactly an eigenstate, then this whole analysis here, this still works. But the phi, or 2 to the little n times phi, is not an integer, but an integer with some extra stuff behind the decimal dot. And what that means is if you apply the Fourier transform, then instead of just exactly getting this basis state here, you're going to get some superposition over different estimates, where the correct one will still have the largest amplitudes. Like like you will get some superposition over estimates, which is going to look sort of like a Gaussian or at least some sort of bell curve around the correct estimate. And that means that if you measure, you're likely to get the correct number phi, or at least some n-bit approximation of the correct number phi, or something fairly close to it. But the calculations are a little bit hairier than what I did here. So we're estimating the number phi. If the number phi needs many more bits of precision, but you're only aiming at an n-bit estimator, then this phase estimation circuit is going to produce a very good n-bit estimator for you. This will not be exactly phi, of course, because phi needs more bits to write down than n bits. But if you have a number, let's say, with n plus 100 bits, which you approximate with the best n-bit approximator, your additive error in the approximation is something like 2 to the minus n. So long story short is this thing is not perfectly going to give you back phi, but it's going to give you back a very good, with high probability, it's going to return a very good estimator of phi, something that has additive error roughly 2 to the minus n. This produces a probability distribution that's concentrated around the best n-bit estimates of the number phi. But you would have to do the calculations, and they're kind of painful, which I don't want to do here. Other questions? Okay, anything online? Okay. So now I guess we'll have a break, and then there's like an exercise session with a few exercises related to the material that I talked about today. How long do we break now? Half an hour, good. Okay, so see everybody back here in half an hour.